table, the motion sensor detected a constant velocity. Ooh. The student interpreted the results and claimed that Newton's second law does not always apply. If you have a constant velocity, that means acceleration is 0, right? If I don't press the accelerator on my car, I keep that speed constant, right? Cruise control. So acceleration is 0. And if acceleration is 0, then the force is 0. So there must be something wrong, he's saying, with this, because the acceleration is 0, that means this whole thing is useless, so there's no force, okay? So he claims that the second law does not always apply. So what explanation best describes why this claim is invalid? All right, so what's really going on is what it's saying in this problem. Well, let's look. A, and this would be, to me, a level 3 question. The 1.5 Newton reading on the spring scale is due to the force of friction acting in the opposite direction to the motion. Since the net force is 0 at a constant velocity, without friction, the lead block would have accelerated at 0.33 meters per second squared. So this comes back to the equation we had written down, right? Force equals mass times acceleration. So what we have here is we have force of 1.5, we have a mass of 0.5, and acceleration here. Well, let's go ahead and solve for acceleration since it's giving me some acceleration numbers. And then maybe I can cancel out some of these problems. So if I solve my equation here, let's close that out. So we divide by 0.5, all right? So 1.5 divided by 0.5 gives me 3. So what's nice about this equation is I can go ahead and use it and know that this and this are both going to be canceled out right away. Get my 2 crazy answer choices out of the way right away. And then look here. I know it has to be either C or D. So let's look at these in more detail. The 1.5 reading on the spring scale is due to the force of friction acting in the opposite direction of motion. Since the net force is 0 at constant velocity, without friction, the lead block would have accelerated at 3. All right, so that sounds okay. All right, but it's complicated. I don't really know about that. Let's see if there's any bad signs in D. Again, you're just looking for bad signs. The 1.5 Newton reading on the spring scale is due to the net force of 1.5 to the right acting on the block, as indicated by the constant velocity to the right. Without this force, the lead block would have accelerated at 3 meters per second squared. Okay. So I'm torn on this problem. So the 1.5 reading on the spring scale is definitely due to the force of friction. That much I know. When you're pulling it along, you're feeling friction. All right, you're feeling it as you're pulling it along. So that would make C sound good to me. However, the 1.5 is due to the net force of 1.5 to the right acting on the block, as indicated by the constant velocity to the right. Since it's moving to the right, the net force must be to the right. However, oh man, that's a tough one. I don't know if I have a good answer for that. So let's bring this up and take a look. This one. All right, so let's take a look through here and see if we can find this exact problem. All right, we have the car thing there, temperature. All right. Bring it down. Oop, there it is. All right, so for this answer choice, it's item 10, and item 10 is, of course it's not going to do it easily for me. All right, the answer choice is C. All right, it says the 1.5 Newton reading on the spring scale is due to the force of friction acting in the opposite direction of the motion, since the net force is 0 at constant velocity. Without friction, the lead block would have accelerated at 3 meters per second squared. A is incorrect because, again, we figured it out, and B is incorrect because of that as well. But D is incorrect because the explanation is incorrect. It does not account for the 0 net force and force of friction in the opposite direction of motion. Okay. So, looking at this really technically, the reason you get a 1.5 reading is because that is the force of friction pulling back. We know the net force here, we know that the force here has to be 0 because the acceleration is 0. So if the force is 0, it's because forces are balanced. So you're pulling it to the right with 1.5 newtons of force, and friction is pulling back with 1.5 newtons of force, and that's the reading you're getting on the scale because it's pulling back against it. And so this is giving you, when again you subtract 1.5 and 1.5, you get 0. So that's why it says 1.5, because friction is pulling against it, giving you a net force of 0, because acceleration has to be 0 with a constant velocity. If this one doesn't make sense to you, as it didn't to me the first time I read it, I wouldn't be too worried. All right. So again, you don't have to get all of these right. That's the nice thing. All right. You're being compared to other kids in the entire state of Georgia, and I don't think there's many of the kids in the state of Georgia who are going to be getting this one right, unless they get a little lucky. Okay. So lucky is good. If you can narrow it down to just C and D, you give yourself a 50-50 chance of getting it right. So that much is good. All right. So please, please, please narrow your answer choices down. Keeping this going, a teacher dropped 3 different objects down a 5-meter vacuum chamber. The teacher then determined the force on each object given its mass and created the table below. What relationship can be determined based on the analysis of the data? So we see a dropping question, right? Where things are being dropped. A couple things I told you about that. Number 1, we got to account for air resistance. What do they tell you? Vacuum chamber. So we have no air resistance. We know that right off the bat. So if you have no air resistance, you know that all of these objects are going to fall at the same time, right? And they're going to hit at the same time, and they're going to fall at the same rate. What rate do all objects fall? 10 meters per sec, check, yeah, gravity, moving fast, or pulling fast, whatever it is. But anyways, you get gravity here. Gravity is about falling things, and gravity pulls on all things with the same amount, okay? 10 meters per second squared. So, which relationship can be determined based on the analysis of the data? Each object has a final velocity proportional to its mass. All right. It does not matter how big it is. In a vacuum, it falls at the same rate. Wrong. Each object has an acceleration due to its mass. No, the acceleration is due to gravity. Wrong. All 3 objects have the same downward acceleration regardless of mass. What do you think that downward acceleration is? Gravity, regardless of mass. That's my right answer. All 3 objects have the same amount of inertia. We don't care about inertia. That's a trash answer. Okay? We're talking about acceleration here. Okay? Because here's the deal. To be fair, we're not talking about inertia, but if you are looking at this, they would not have the same amount of inertia. Inertia depends on mass, so it can't be regardless of mass. All right, so the only answer choice you have here is C. All right? And you know that falling objects, downward acceleration due to gravity is always the same, especially when there is no air resistance. All right? Keep it rolling. A student investigated the energy transformations that occur when a call is placed from cell phone A and received by cell phone B. The student drew a diagram to show this process. Call is placed from cell phone A, person talking, all right, and then goes in the phone. The phone transmits the frequency assigned to it by the base station. All right, so it transmits to the cell tower, which transmits to the base station. All right, the frequency is received and retransmitted on cell phone B's assigned frequency, goes to the cell tower, and received by cell phone B, where it plays in the person's ear. So we know enough about these kinds of cell phones to know that cell phones are a type of microwave. All right, so we got microwaves going on in here somewhere, and that's at least somewhere to start. So let's look at what they want from this question. Based on the diagram, what evidence is there for the transformation of chemical energy into electrical energy, and what other energy transformations must occur for the call to be received by cell phone B? So this is a 2-parter. We're looking for transformation of chemical energy into electrical, and then which other energy transformations must occur for the call to be received by cell phone B? What else has to go on here to get into that? Well, let's think. Chemical energy into electrical energy. You know chemical energy has to do with movement, or actually not movement, has to do with food, all right, has to do with gasoline, and it has to do with batteries, all right? So, chemical energy into electrical energy. If we're going from chemical to electrical, odds are we're dealing with a battery. So, let's look and see if we have answer choices here dealing with batteries. All right. So A, evidence. Cell phones are powered by a battery that produces electricity to send and receive calls. That looks good to me. Cell phones are powered by a battery that produces electricity. That looks good to me. Base stations are powered by a battery that produces the electricity to receive and forward a call. Do you think an entire base station, an entire cell phone tower station is based off of a battery? No, that's plugged in straight to Georgia Power. So therefore, that's going to be, well, coming from what? It still would be chemical to electrical, but not because of the battery, but because of the coal that we use. But anyways, that's why this one's going to be incorrect. Because base stations are not powered by a battery. You should know enough to figure that out. All right, so we know that C and D are not the answer. Let's look at A and B. Those are my two trash answers. Here are my good ones. So let's look at transformation 1. Sound energy is transformed into electrical energy by the cell phone. Or transformation 1. Sound energy is transformed into electromagnetic waves by cell phone A. Okay. I mean, I could see the sound being made into electrical energy. I could see that because it's in the phone. All right, I guess, well, sound energy is transformed into electrical energy. That means that the sound is making electrons move. I don't know if I can say that that's true for sure. So let's look over here at B. Sound energy is transformed into electromagnetic waves by cell phone A. Well, I know that a cell phone takes my sound and converts it to microwaves, which are a type of electromagnetic wave. All right, well, let's look at transformation 2 here. Electrical energy is transformed into mechanical energy in the cell towers. Mechanical is movement. That can't be right. So let's go down here to B. Electromagnetic waves are transformed back into sound energy by cell phone B. That sounds good. Yeah, so if I go sound into microwaves, right? The microwaves go to that cell phone, right? And then transmit it back into sound so they can hear me. So this one is the most complete answer. If you're getting choice A, it's because you're not reading all the way through. And if you're getting C and D, it's because you're just not thinking about the problem. Base stations are powered by a battery. Don't feel, and this is the one thing I tried to tell before, don't feel bad for an answer. Don't feel like, oh, the poor answer, well, it could be correct. Maybe it is, maybe it doesn't. No, it doesn't have a battery. You know it most likely does not. Don't make excuses for it. If it's trash, it's trash. Okay, throw it away. Focus on the ones that make sense. All right? Excuse me, that was B. Okay, so student pulls a lever down 4 meters. The lever lifts a box that weighs 20 newtons up, a distance of 2 meters. How much work was done by the box? Or done on the box? Okay, so work equals force times distance. All right, so how much force did I apply? And how much distance did it move? Now here's the deal. What are we trying to do? We're trying to lift this box up, right? So the question becomes this. It lifts the box up 2 meters, but she pulls down 4 meters. So the question becomes here, which do I use? Well, this is where it gets really complicated, so stay with me here. Now, if I'm lifting a 20 Newton box of 2 meters, well, 20 Newton box, 2 meters, that gives me 40 joules. And that is the right answer, okay? I don't care about her, I care about the box. I'm lifting the box. The box's distance and the box's force, okay? However, she's using mechanical advantage here, right? So she's got a distance of 4 she's pulling versus a 2 meter distance she's trying to pull it up. So she's got a mechanical advantage of 2. That means that if she's lifting this 20 Newton box, she only has to use 10 newtons of force. So for her work equals 10 newtons of force times 4 meters, which is still 40 joules. And this is the thing. The amount of work is always going to be the same no matter which one you use. You just got to think about the force being applied. Either it's more or less depending upon the mechanical advantage there. But the answer is definitely B, 40. Okay? All right. Now, rolling this on through. A student collected the thermal data for acetic acid, vinegar, and water and graphed it in the heating curves for the two substances. So you can see the heating curves. Up, over, up, over, up. Up, over, up, over, up. Now, it looks like the dotted line is vinegar, acetic acid, and the straight line there is water. All right? So, there's a big difference there in some of these, okay? What's happening to acetic acid between points X and Y on the graph? Let's come up here and look at acetic acid between X and Y. So we have a flat area. You guys know from what we've done that a flat area means a change in state. So if we look at the flat area there, that means this is a solid. Flat area means it's going from a solid to a liquid. So we got melting going on right there from X to Y, right? Okay. So what's happening to acetic acid between points X and Y? If it's melting, we're going from a solid. It's becoming warmer as it absorbs heat energy from the surroundings. The solid is converted from a solid to a liquid by absorbing heat energy from the surroundings. So yeah, it's not that it's becoming warmer. That's what's going on here from 0 to X, okay? From X to Y, it's converted from a solid to a liquid. So A and B are your two trash answers. It's not starting in a liquid. But for C and D, you got to choose between them. Well, the solid is not going faster and faster and faster. It's actually starting to transform into a liquid there. Okay? For question 23. All right, same thing. Which comparison can be made about a phase change common to both based off the graph? So let's look at phase changes here. That is from X to Y, and then these lines, wherever we got a zero slope there. So more heat energy is required to melt a gram of acetic acid than melt a gram of water. To melt a gram, more heat energy. All right. Let me see. To melt, let's see, heat energy added. So you need about up to almost 400, and then maybe about 300 there. So yeah, I mean, you could say A, more heat is required. More heat energy is required to vaporize a gram of water than to vaporize a gram of acetic acid. Oh, I'm sorry. A can't be right. More heat energy is required to melt a gram of acetic acid. Acetic acid only takes, let's say, like 200 there, and this is almost 400. So water is the longer one there. So water takes more energy. So it can't be A. So A is out because it takes more energy there, right? Heat added. Longer line, shorter line. All right? More heat energy is required to vaporize a gram of water than to vaporize a gram of acetic acid. So let's look at vaporizing here. More energy is heated for water than acetic acid. Well, let's look. Water's got this whole long line of heat added to vaporize. That's got a short line. So I think B here is correct, because it does take more heat to vaporize a gram of water versus acetic acid. So just be careful and double check. As you can see, I might have missed this one if I didn't go back and look and make sure that I was talking about the right thing, because less heat is required for acetic acid versus more heat for water. And up here, more heat for water than for acetic acid. And just to be sure, let's look at these two. Given the same amount of added heat, temperature of a gram of water will increase at a faster rate than a gram of acetic acid. Now, acetic acid's got a greater slope here, so it increases temperature faster. And the same rate of heat loss, the temperature will decrease at a slower rate than a gram of water. No. Not only will it increase temperature faster, it will decrease temperature faster in reverse direction. So those would be two bad answers. All right, 24. A student drew models of an electromagnetic wave and a water wave. Which scientific question did the student most likely ask about how to draw these models? So, when I see electromagnetic wave and I see a water wave, I want to look at these two things and see how they're similar. Well, both of these, you can tell right off the bat, go up and down. What kind of waves go up and down like that? Transverse waves, right? So we know we have transverse waves going on, all right? We know that all waves transfer energy. Those are some similarities there, all right? EM waves, we know happen, or can happen in a vacuum. So they know actually something about a vacuum. And water waves, again, just transfer energy. That has a medium there. Okay, well, let's look. Are water waves and EM waves examples of transverse waves? Which scientific question did the student most likely ask to know how to draw these? Okay, well, are they both transverse waves? And then they drew these. I guess you could ask that question and then draw that model and be like, oh yeah, they're both transverse waves. So I guess that one could work. Do water waves travel at a slower speed than electromagnetic waves? Does either of these models deal with speed? That's why that's wrong. Neither one deals with speed. Can water waves and EM waves travel through different media? To be fair, that's an okay question. And I do see two different possible media here. All right, so let's say this one's a possible. How do water waves and EM waves increase their amplitude? Well, if you look, the amplitude for both is the same, right? From the rest of the crest. So, yeah, I don't think that's going to be an answer choice. So those are your two bad answers, and these are your two close ones. Can they travel through different media? So if they travel through different media, right, we probably see them going through different media. I only see one medium here and one medium here. That's not enough. The simpler answer here is, are they both examples of transverse waves? Doesn't this model show that more? You see what I'm saying? It's which model shows it more. And so I'm going to say A here. And I think that's the correct answer. Okay? Which one shows it more? Don't make excuses for it. Find the one that's definitely true. And that's where you get your answer from. Okay. Oop, change it. There we go. Moving on down. A table compares two different light-emitting diodes, LEDs. Based off the data, what can be identified about the energy of the waves emitted by the LEDs? Green, diffused, and gallium arsenide. Wavelengths and current. Okay. What can be identified about the energy of the waves? All right, the wave energy of the green diffused light is 1.65 times that of gallium arsenide. All right, so let me see. 1.65 times. That means there's a formula there between wavelength and amps, V equals IR. I don't think there's any equations that work with this. What I do know, though, is that wavelengths, right? Shorter ones have higher energy, right? Yeah. So if I look here at green diffused LED, we have 1.65 times that of gallium arsenide. Well, let's look. Green is a short wavelength, therefore it must have more energy. And if I look at these, this shows that green has less than 1 on those two, right? Therefore, these two must not be the answer choice because they're less than 1, which means it would be smaller. Yeah, so it's got more energy, therefore it must have a certain number bigger than 1, right? So the question becomes, is it 1.65 or is it 3? Well, one way to find that out is to take 930 and divide by 565. That will tell me how much to multiply by. And I get 1.65. So 1.65 times 565 will give me that number. Yeah. Although I think this is the correct answer, although I think I did do that weirdly. But yes, that should be the answer we get. Yeah, because the energy is that bigger. Even though okay. But yeah, okay, I'm not going to confuse you with that one, but that's why and how we got it, okay? It needs to be bigger, so that's going to be the bigger answer, okay? All right. Rolling this on down. 26. A student is investigating the difference between light waves and sound waves. The student does this by filling it using a capsule filled with solid glass at one end and a vacuum at the other end. The student will transmit waves into the capsule at a 30-degree angle to the normal line. Which two questions should the student ask and which predictions are most likely correct? Here's what I'll tell you. When they give you question prediction, odds are the answer is always going to be in that prediction. If you know your science, look at the predictions. You don't even need to know what the questions are. Okay? So, let's look at this. Just predictions. Ignore the questions, just predictions. And it says which two questions should they ask. So let's get predictions right here first. So EM waves and mechanical waves will continue through a vacuum at a lower speed. No, absolutely not. Because mechanical waves are sound waves. And sound waves need a medium. They cannot go through a vacuum. All right, let's look at B. The EM waves will travel in a straight line, showing that they have maintained a constant speed. So if I have an EM wave and it's traveling from one medium to another, like I see here, solid glass vacuum, I know it's not going to be no straight line. So this is not right. All right, that's trash. And this one is also trash because, again, it can't be a straight line because it will not be a constant speed. It's changing mediums, right? Or media. Now, prediction next one. EM waves will continue through the vacuum while the mechanical waves will go no further. Now, that's possible. Mechanical waves can't go through a vacuum, so that sounds good. Let's look at the predictions here. Both EM waves and mechanical waves will bend, showing that they have passed through each medium. Now, the mechanical waves will definitely bend because you got refraction going on here. However, mechanical waves can't go through, so that one cannot be an answer either. All right, so we're left with C. I don't care about the question. The EM waves will bend downwards, showing they have sped up slightly. So, nothing about mechanical waves. EM waves will bend downwards. There's some bending going on there. Let's look at it in a second to see, just to make sure that it's going to speed up, all right, as opposed to slowing down. And then the EM waves will continue through the liquid medium while the mechanical waves will go no farther. Well, let's look. So it says through a liquid medium. If I remember right, I look up here. I don't think it's liquid. Oh, Lord. We're all the way down at the bottom. All right, so let's come back up here to this. Let's take a look. So yeah, look, solid glass and vacuum. So there's no liquid. Therefore, I can go ahead and eliminate F. So the EM waves will bend downward, showing they have sped up slightly. Well, let's look. If I move from solid glass to vacuum, that means I'm getting thinner. So it moves towards the normal one, it's getting thick. That means it moves away from the normal when it's getting thinner. So that's the pathway it should take, so it bends downwards for sure. So that gives me C and E. Okay? All right. I didn't even look at the camera there. That was really weird. All right, so C and E. Okay. 27. A student is modeling an electric circuit containing 3 light bulbs and a battery. Which model shows a circuit where the current flowing through each bulb will be the same as the current at point X? All right. So when you're dealing with these kinds of models, the main thing is this: when you're talking about the same current, all right. When you line everything up in a series circuit like this, the nice thing about it is the current will be the same all the way through because the electrons all go through the same path. Okay? Over here, they're going through different paths, multiple paths, different things lined up. Okay? So when that happens, it affects the actual current. All right? So I don't want something with multiple paths. I want something with a single path where the electrons are all experiencing the same resistance all the way through. And the only place that happens is at D. Because, again, I'm on one pathway. Therefore, the current will be the same across the entire pathway. Does that make sense? So this will give us answer choice D. All right, question 28. A student did an investigation to determine the effect of a magnetic field on a moving steel sphere. The student recorded the motion of the steel sphere on trial 1 and then drew the desired motion for trial 2. So we got trial 1 and then trial 2. Desired motion. This is what they want. And if you look here, we get more of a curve than that one. All right, so therefore, if I'm getting more of a curve, that means I'm getting more of a magnetic field, which means this one must be stronger. All right, and does everybody understand why? You get more of an effect of the particles, therefore it must be stronger electromagnet here. So, if the steel sphere has the same initial velocity in both trials, which action would best help to achieve the motion in trial 2? Well, I want to have more coils because more coils means stronger magnet. Put a resistor between the battery and the switch. If you put a resistor in there, you're not going to have as many electrons flowing through. Fewer electrons flowing through means less of an electromagnetic pull. Or push, I should say. But anyways, that's not going to work. I don't want a resistor. I don't want to slow the electrons. I want to go faster. I want a bigger battery. I want more coils. I want a bigger iron core. Those are the things I want. Replacing the nail with one made of aluminum. Aluminum is not magnetic. The only 3 things that are magnetic are iron, nickel, and cobalt. Now steel, the steel sphere, steel is a combination of iron and carbon, I think. But it's got iron in there, that's why it's affected by it. So B can't be it, not aluminum. Reversing the direction of the pole on the iron core. If you reverse the direction, then it might go the other way. Or I guess it might still come the same way, but you're not going to affect anything by reversing the direction. That's not going to make as big a difference. Increasing the number of coils of insulated copper wire. If you need a bigger electromagnet, you know you need more coils. That's the deal. Question 29. A parallel circuit contains a battery with a voltage of 9 volts. The total resistance in the circuit is 18 ohms. Which claim about the current in the circuit can be supported mathematically from the relationship between voltage, current, and resistance? So, I don't know what else to tell you other than a parallel circuit contains a battery, voltage of 9 volts. The resistance is 18. What claim can be made about the relationship? Well, if I have volts and I have resistance in ohms, and then what claims can be made? Well, I'm looking for I here, so let's plug these numbers in. I get 9 volts, I get 18 ohms, and I. And if I solve for I get a current of 9 divided by 18, which is 0.5 amps. So, I need something with 0.5 amps, and if I'm looking through here, there's only one answer choice I see with that, and that is A. All right? And again, it's I equals V divided by R, and that's what I did. I took the voltage and divided by resistance. And that's it. Oh, well, submit anyway. All right, so if you're going to answer questions, submit anyway. And, yep, just those 3 that I guess I just didn't type in. So, anyways, that is this in a nutshell, and I cannot stress to you enough. When you're watching this back, please look at your answer choices. There's 4, right? 2 bad ones, 2 close ones. Make sure the science is good in the answer choice that you make. Don't make excuses for them, okay? If they're wrong, they're wrong. Find the one that makes the most sense, that has the most, not even makes the most sense, that has the most scientifically accurate information that you don't have to make excuses for to make it be right, okay? It might be right if, it might be right when. Don't say those things. It's only right in the situation. That's what matters. And if they give you questions and predictions, the questions are nice, but you don't need them to answer it. Look at the predictions. Look at the science. Know your science. Go through, eliminate bad answer choices, and you'll be good. Again, answer all the easy ones first, and then the harder ones at the end. Okay? Love you guys. Good luck. Please come see me if you need any help, 4th period or in the mornings the next couple days. Okay? All right. Love y'all. Have a good one.